everyone. My name is Maria Liapopoulou, and today I have the pleasure of welcoming you all to our talk with the title Pushing Boundaries: The Role of Nonlinear Response History Analysis in Seismic Design. This is organized by SECED Young Member Subcommittee, and we have today two speakers, David Shook and Ricardo Henoch from SOM San Francisco office. Let me start with some basic housekeeping rules. I would like to ask the audience to please keep your cameras off and your microphones on mute for the duration of the presentations. We will have a Q&A session after the presentations. And if you have any question in the meantime, please feel free to type it in the chat. Also, please remember that today's event is being recorded and it will be uploaded on our SECED YouTube channel. So, by dialing into this event, you agree that any information or views you share will be made public. Now, an announcement from our SECED Talks podcast. We have recently launched a new series of episodes on first steps in civil engineering dynamics, where we explore the day-to-day responsibilities of early career engineers. And we have launched the second episode of this series. It is an interview with Francesco Morfuni from Nucleo, who is being interviewed by Ziad Khalil from Imperial College London. I would like to thank here the contribution of the rest of the members of the podcast team, including Philip Zinkiewicz from Atkins Realis, Hank Lee from Atkins Realis, Ludovica Pieroni from UCL, and Evangelos Infantidis from Holtec Britain. This is available now on our Spotify and YouTube channels, so please check that to learn more about this episode. Our speakers for today's event are David Shook and Ricardo Henoch, both associate principals at Skidmore, Owens and Merrill, SOM San Francisco office. David has a long experience covering post-tensioned floor systems, seismic performance, and sustainability. And his design experience includes large-scale, iconic international towers. He is a frequent lecturer at universities and conferences, and he is the co-author of a book published by the Council on Tall Buildings and Urban Habitats with the title Performance-Based Seismic Design Guide. Ricardo also has a long experience on steel and concrete, covering performance-based seismic design and extreme loading and events. He has recently been involved in the Earthquake Engineering Research Institute group to evaluate the performance of hospitals in the 2023 Turkey earthquake, and he has experience in design of tall towers in China, residential buildings in high seismic regions in west coast of the USA, and historical retrofit buildings. So without further ado, I would like to ask David to start the presentation.
Glad to. Thank you for the introduction. And I'm going to try to share. I think I'm sharing. Are we good?
Yes, we can see it. Perfect.
Great. Well, thank you for having Ricardo and I today. We've been looking forward to this presentation and some discussion later on. It's great to see so many people joining. I saw Jerry Fu there from our London office, so good to have you, Jerry, and not everyone else there in the UK. Thank you for joining. Ricardo and I have been practicing on the west coast of the US, particularly in San Francisco, but we've done projects, and we'll talk about some of our international projects. But pretty much all of our work has been in seismic design. I think I really only had one non-seismic project in my career, so we're very orientated this way, and it's great to see a group of young people very interested and focused in understanding seismic design. When I started at SOM, I guess it was 17 years ago, there was in the practice of seismic design, there was a lot of restrictions. a lot of you can't do this, you can't do that, you can't do this. SOM was really unique in that we were pushing boundaries back then, I think in a unique way. And there'll be a little bit in the introduction about that, but we'll spend most of our time talking about how I think the script is kind of flipped. And I feel actually more empowered in seismic zones now than I do in non-seismic zones, which sounds very strange. But the profession has moved dramatically using nonlinear response history analysis, which is what we want to talk about today, how nonlinear response history analysis helps us in seismic design, how it changes the way we think and we approach everything that we're doing. So with that, I'll kind of get into it. We'll talk about two projects today. The one on the left is in San Francisco. I would say it's a very classic high-rise seismic design on the west coast of the US. And it will highlight the importance of nonlinear response history analysis, even when you have a somewhat conventional building. It's a beautiful building, but it's still conventional. And then the one on the right, Ricardo will talk about in Suzhou, that we would not have a chance of having confidence in our design without nonlinear response history analysis. And it is so exciting, all of the features of this building that have been brought together to solve architectural and structural challenges. So just a little introduction about our firm. As I mentioned earlier, some of you on here know SOM, some of you don't. SOM is very well known for tall buildings. We've designed some of the tallest structures or the tallest structures that have ever been constructed for people. And we continue to do a wide range of tall buildings. And we've been doing them for a long time, going all the way back to Sears Tower and John Hancock in Chicago. Burj Khalifa, of course, is well known. One World Trade Center. A little more recently in New York, and a wide range of high rises in China over the past 20 years. We approach design from the viewpoint of, look, everyone loves the building on day one, okay? It's just like a new pair of shoes or something, you know, it just feels good. You're glad to get in there. But we want to design buildings that are great in the future. And we work with our in-house architects to do that. And the award that we consider super important is a AIA 25-year award. They're similar in the UK where buildings are loved, kind of like Broadgate, which is nearby here. This is the Exchange House, of course. These are well-loved buildings within SOM, and we feel that people in the area can still enjoy them 25 plus years later. We do things other than tall buildings. This is a airport in Saudi Arabia, of course. This is another airport in San Francisco, and this is a really interesting one that was done when I started at SOM, but its ethos was still resonating within the firm. This was a project that's base isolated, so that whole beautiful international terminal you see there is not possible without base isolation. And base isolation really requires nonlinear response history analysis. Now, when I was starting at SOM, how to do nonlinear analysis with base isolators was well established. And we were using that. And we were being creative with the structure and the design and how people interact with the design on a day-to-day basis, completely enabled through nonlinear response history analysis in a high seismic zone. Another project, and when I started at SOM, like I did like the very last RFI on this project. So I like to say I worked on it, even though I didn't really work on it. But it's a beautiful cathedral. It's in Oakland, super high seismic area, poor soils. And this is a very low budget project, okay? And it was going to be something totally different than this. But we were able to incorporate, again, base isolation and enable a completely new architecture with incredibly low cost. I can't tell you how, I hate to call the building cheap because it's a beautiful building, but this is a very low cost building for the Oakland Diocese. And it was enabled through base isolation, and base isolation was and is enabled through nonlinear response history analysis. So you can't do these architectures, these structures, these beautiful places. Like you can't even tell what the structure is. There's no cladding on this building. It's just It just is. It's the materials that are very honest. So were very well loved and celebrated within the firm, and we were expanding our creativity at the time pretty much with base isolation through nonlinear analysis. I know I've said it like 20 times. All right. Coming a little bit more to the current. This is a building that is finished in San Francisco, but it does personify and represent very classic use of nonlinear responses trade analysis, especially on the West Coast. So the project is 500 Folsom. It's a 43-story, it's feet. I'm sorry, Ricardo and I live in the feet and inches world, but 43 stories, as a large podium, very deep basement, a pretty large building, but pretty conventional in a number of ways. The design was done in a way, and this is just good seismic design. It looks very simple, like what you're looking on the screen. You're like, oh, it's a concrete box. That is not easy to achieve. It takes a lot of coordination with the architects. And the best performing structures have the clearest structural concept and execution of that in the design. So this is just a concrete box all the way up and down. Sounds very simple, but we spent a lot of time coordinating elevators, stairs, MEP, because we got to get those doors to stack. We got to get the pipes going in and out in the correct places. Because if they're not, they're going to be detrimental to the seismic performance of the building. It's an all concrete building, post-tension floors. Here's just kind of a diagram, kind of layers in the deep basement that goes along with it. The soils were, other than Mexico City work, the most complicated I've ever done. Mexico is its own thing, but other than Mexico, the most complicated I've ever done. And this is a cross section through the site. The building would kind of be where that blue box is there. And it went from kind of near rock to clays to liquefiable soils, which is kind of what this thing is. All kinds of soils across the site, very complex. Yeah, and there was liquefiable soils in there, which we had to remediate. We're going to start kind of in the ground and work our way out, if you're wondering. So there was soil improvements done on the site to basically create these unreinforced concrete soil slurries that made this kind of grid. That's what all those circles are there. The red lines indicate where the concrete walls are. So that when the soil liquefies in an earthquake, we have a good bearing pressure to get down to the non-liquefiable soils below. So the foundation is a reinforced concrete mat. It was not done with piles. If you're wondering, we're about a block from Millennium Tower. That's a whole other thing. But we had great performance, both with the seismic analysis and then the later construction using, I think the term in the UK usually is raft foundation. We usually say mat, but a raft foundation without piles. So the podium, this is the podium plan. There's some additional walls in the podium to help balance torsion because those masses that are kind of sprawling out from the core cause torsion. Now, early on, we had a very slender core. This is actually, you can see a different core than I was showing earlier. This was the first core represented by our architects. And I about had a conniption when I saw it because it is not an efficient core. It was so slender, we actually considered outriggers. And outriggers is when the core leans on the perimeter columns like you might do when you're skiing in a lateral event, wind, or earthquake. And they're kind of needed when you're like 80 plus stories, you kind of need them. But 40-story buildings shouldn't have outriggers. For a lot of reasons. So, you know, we tried to make it as efficient as we could. This is a little bit of an aside, and then we're going to come back. Okay, this is like a little deviation, and we'll come back. We use topology optimization. This is a free software you can get. It's part of Grasshopper. There's a tool in there called TopOpt. Highly recommended. Even if you're not proficient with Grasshopper, you can figure it out in an afternoon. And the red and the blue kind of tension compression, it tells you where the material wants to be. This is a whole other presentation. I won't get into it. It's just a tip of the hat. Use topology optimization to help you think about structures. It's a wonderful tool. Now, we went back and worked with the architects, and we made that core a little less wide, a little deeper. We got up to 33 feet. The width to the height of the core is 12 to 1, or the height to the, and we were able to get rid of the outriggers, which was really good. And we were able to get all of that vertical stuff, stairs, elevators, all of that into a single core with openings that stacked all the way up and down. Good seismic design, very conventional dimensions, the spans, the post-tension slab, the shear walls, all very conventional for West Coast high-rise design. This is showing the 4 shear walls in their elevations. The darker zone are boundary zones, and we'll talk about those in a minute. This is kind of a section through the building, so you can kind of see it from that raft foundation all the way up. Very simple design, but it took a long time to get there. So this is when this kind of a younger crowd here. So, you know, this is very much, if I were to give one like lecture in a class, you're about to get it. Okay. So we designed this with response spectrum, classic response spectrum. Very, it's all linear. Okay. The first iteration is done with response spectrum, and then we went into nonlinear. And when we designed it with response spectrum, it was perfect. You could not ask, other than it being a little soft. It was a little soft building, a little on the soft side. Other than that, this is exactly what we want to see. If I follow the code and do exactly what the code wants me to do, other than a moment frame, which this building has no moment frame, this is what we want to see. And frankly, if we had a moment frame, it wouldn't be any different because the moment frames in high seismic areas and tall buildings, moment frames don't do a whole lot. When there's a core, of course. So we had our periods well delineated, 5.8 seconds in the soft direction, 4.3 in the strong direction. Torsion was way down at 2.6, which is great. This is exactly the kind of behavior we want to see in modal analysis, which of course is the preamble to response spectrum, which is what we do response spectrum as an initial run. So when we look at the building drifts, I'm not going to go through some of the detail on this, but when we do response spectrum in high rise, we will often use the 2,500-year earthquake. I won't go into kind of the details of that, but it's helping us understand a few things that we wouldn't understand if we were doing the code level earthquake. Either way, the drifts were great. Okay, torsion was good, drift was good. This building looks beautiful. So because we only have a core, that central box, because we only have a core in the US building code, we're supposed to have a perimeter moment frame, but they're expensive. They don't do a whole lot. So you almost never see them on the West Coast anymore in a high-rise building. It's part of what's called a dual system in the US code, and it's in a lot of codes. I'm pretty sure it's in the Euro codes as well. And the concept is, well, we don't really know what the core is going to do, so we're going to put a moment frame just in case. That's why it's there. It's a backup plan, right? It's all these beams and all this detailing and all this material as a backup plan. So in the US over the past 20 years, we have done more analysis in our designs than required by code. Code requires response spectrum. We're doing nonlinear response history analysis, and we're having a peer review panel. And because of those two things, it's become standard to remove that moment frame, which was belt and suspenders anyways, and then really understand what this core is doing. We're going to model the nonlinear behavior of this core. When I say nonlinear, yes, we're doing P delta. Okay, yes, we're doing nonlinear soil springs. I'm not talking about that. I'm talking about the nonlinear material behavior of the steel and the concrete. The steel and the concrete in that core, we are going to model with representative elements. So on the far right is our Perform 3D model. We don't really use Perform 3D anymore. We use ETABS. That's a pretty recent transition we've gone to, but it's basically the same thing. They've just rolled all the Perform 3D stuff up into ETABS. The concept is, and you can see it in this diagram on the top right or top center, is that the boundary zones like right in here. We'll see more of what a boundary zone is in a minute, but it's additional rebar, additional detailing for tension and compressive behavior at the end of a wall segment. So we'll have boundary zones, say here, we'll have them at the corners, of course, because the whole box is working right. But we'll also have them adjoining doors because, yeah, it's a box, but it's not a rigid box. It's almost like a confederation of pieces that kind of work together and kind of don't. Okay, it's not a perfectly rigid box. Those openings make it kind of soft. So all of these redder areas are where the boundary zones are going to be. Again, you'll see some images of that in a minute. But we model the tensile behavior of that with fiber elements and compressive behavior of that with fiber elements. So we understand the nonlinear tensile behavior from the rebar and the nonlinear compressive behavior from the concrete. So both are being modeled nonlinearly. We monitor strains, deformations at these blue dots, and all of the coupling beams. Each one of these doors has a beam going across it. We won't spend a whole lot of time on it, but we model the nonlinear behavior of that as well. So that center core is kind of, I'll say, fully nonlinear model, top to bottom. We'll do some nonlinear modeling in the columns and slabs a little bit. I won't get into that so much, but we're really just monitoring the behavior of the gravity system and making sure the gravity system isn't getting in too much trouble. But the main focus is on the lateral system. So this is a representation of all of the earthquakes that we ran. Okay, well, actually, this is half of the earthquakes, but this I won't go into that. We ran 22 earthquakes. This is 11 of them focused on short period behavior. There's 11 other ones focused on long period behavior. And the way it's done is each one of these lines is an earthquake that is representative for our site. And we do we create a response spectrum for that so that we can understand for each earthquake what kind of short period behavior does it have? What are the higher frequency motions? And what is the long period behavior that we have going on? And our building, these red lines represent the primary periods of the building. So the building is really paying attention to and resonant here. The building is very resonant here, and the building is very resonant here. The building doesn't really respond a whole lot to this stuff, and it doesn't really respond a whole lot to this stuff. It really responds kind of, say, right around each one of these red lines. So one area that we had some difficulty with, and you'll see in a minute, is we had a couple of ground motions that were pretty high, very representative of the site, and I would say the top seismologist in California, Norm Abramson, agreed these are appropriate ground motions for the site. We're very, very high. In fact, the code spectra would be down here, and those ground motions are way up there, and pretty close to one of the resonant periods of the building, which is quite difficult, right? So when we went about the design of it, we initially had, I would say, a heavy rebar scheme, which is kind of this dotted line as you go down here. This is the height of the building. This is the total vertical area in the core as a percentage of the concrete area. And the initial design, we actually had pretty high levels of reinforcement. And when we ran nonlinear analysis, we didn't see very much yielding. And as you'll see in a minute, we actually had some really bad behavior. We actually reduced the rebar significantly over the height of the building and improved the performance. I'll show a little bit more of that in a minute. And we actually isolated an area for a hinge to occur. And a hinge is when we reduce the rebar notably from the areas above and below to focus nonlinear behavior in a particular area. So this plot is the vertical axis is height on all three of these. This is rotation of a coupling beam, which is highlighted right here. This is strain, which is axial tension and compression adjoining that coupling beam. And then this is the inner story drift. So the one on the far right kind of represents overall building behavior. The one in the middle represents the boundary zone behavior, and the one on the left represents the coupling beam behavior. So if you remember the initial design we had per code was this dotted line. Then we reduced it, and then we actually created a hinge. So you see when we designed it, actually per code, we got drifts up to 5%. Now this is a 2475, so we can go up to 3%. 3% is the limit for the average, but we had an individual ground motion get up to 5.5%. Totally unacceptable. Like, no way is that okay for even one ground motion to go that high. We actually, when we reduced the rebar, we increased the ductility and therefore reduced the response. So you reduce the rebar, you reduce the drift because you're increasing energy dissipation. Then when we looked at the strains in the core, particularly at this critical spot, when we reduced the rebar, we increased the ductility, therefore reduced the tension. And lastly, we had this whole bay of coupling beams actually fail. Okay, and this is a code-based design, right? That moment frame isn't going to do anything, believe me. Okay, I know there's no moment frame, but that's the only thing that is taking exception to the code. This coupling beam isn't just one, it's all of these are done. Like this is totally unacceptable response, and it's a code-based design with a realistic earthquake on it, okay? We reduced the rebar in the shear wall. We actually increased it in the coupling beams, and we saw a dramatic reduction in rotation because the energy dissipation was increased. This is a little bit of what a boundary zone looks like. And we actually came up with some criteria to map that strain and the tension and compression strains to the shear walls. And we actually did this kind of just like on our own. We were super interested in this. And when we presented it to the peer review panel, we didn't know it at the time, but there was a group out there actually going to propose this to go into LA tall buildings and eventually ACI. And we actually matched very closely with them, which was great to see that. But here you can see all these different colors, I'll say, are different types of boundary zones, different types of reinforcement, and we're pulling that strain information, tension and compression data from all those fibers in that nonlinear model, and we're mapping all different types of detailing to the building based off its response, which is just absolutely wonderful to be able to do that. Because the code, you see all this orange stuff up here? That's a lot of extra detailing the code would tell you you don't need, but we actually need it. All right. And because we reduced the rebar, we had a very happy owner. He saved about $500,000. So that's always good. Here's just a construction image before I start to turn it over to Ricardo. You can see these boundary zones going up, the coupling beams. They put these diagonal bars in there for energy dissipation. And here's a picture of the building finished and just kind of walking around on the podium terrace. Beautiful building, fully occupied in San Francisco, which is actually kind of rare because of the whole dynamic going on in the city. So very happy owner and successful building. Okay, Ricardo, do you want to share your screen to do your part? Okay, I'm going to stop sharing then. All right.
Let me know if you see my
and
screen.
we'll have time we should have time for a few questions at the end.
Yeah. So do you see my screen?
Yes.
Okay.
Yeah, we can see it.
So we'll move to a complete different zone in the world where projects in scale are quite large, very fast-paced, and where decision makers aim to, when you're proposing something that's different, they need the right amount of information in order to move forward. So this project is in Suzhou. Suzhou is a city close to Shanghai on the western inland from Shanghai. And it's a very beautiful city surrounded by canals and lakes, and it has an awesome view. So the owner want to create something very unique. It's a 460-meter tall building in this water city, so they want views. And in the past, we've done several typologies of mixed use where the tall building wants to have office use and apartment use, or sometimes even a hotel. But this building was very unique because the ratio of those different usages changed dramatically. And now they wanted something that's more common nowadays. I see many projects that the residential part takes priority over the retail or office area. And that's what Suzhou was all about, like 80% apartment, 20% office space. But that creates a constraint in the planning of the core and the area of the project. So when you have a residential tower, you have a target area, and you can only have a certain amount of depth before your apartment becomes kind of a very dark environment. And if you offset that from your target area, you get too much core. It's not effective. But if you do the opposite, you start with an efficient core like David showed, like a very efficient core that's taking everything, and you offset the required amount to create the residential space, well, we don't have enough area for what the client wants. So that's kind of the conundrum that we have. We want both, but in different ways. So the provocation started with the architects highlighting this challenge and creating a parametric kind of investigation on what was the most effective perimeter to meet this demand. And with that perimeter, we quickly reach out to a solution that we're quite familiar with other taller buildings, which is a tripod. The tripod allows us to have higher perimeter and also a core that could be effective. But this project wanted to be different, so thus we created a tripod 2.0, where the pedals get detached in certain key elements and to serve the different programmatic needs. So the shape form on the very top, it's where most of the programming is the residential. Then we have amenity areas where we connect each one of the pedals. But having this open area allows to reduce the wind load of the structure very dramatically. Our preliminary analysis of this shape showed that we could reduce the wind loads to 29% just because of this opening. So that was quite significant for this tower. In the end, the main idea of this building was to utilize simple structural systems connected together to be able to match the design intent. In the central part, a core, a reinforced concrete core that tracks along the height, several coupling trusses that connect each one of these pedals together to act as one. A moment frame, unlike what David just expressed about the avenue or the exit path that we have here in the US for getting away from a dual system in the Chinese code, even though we are going to a similar process. It's not called peer review, it's an expert panel review where several experts review our work. They don't allow to deviate significantly for the code, and we are kind of forced to use a dual system. So therefore, a moment frame is required through the height of the tower. And we have different typologies of slab throughout to provide the service, and that creates the overall system of this particular project. The idea is that we utilize the materials in a very systematic way and cost-effective way too, where the heaviest ones are used on the base and the lighter ones on the top. So we start with an RC system on the bottom for the office plan, and then we try to align the framing layouts with the partition layouts of the proposed tenant that they're going to have in those areas. And then on the residential areas, we have a metal deck and steel systems that also are deeply coordinated with the programmatic residential units that we have on the top. And in the amenity zones, we have a lots of composite system because we need to have stronger diaphragms to connect and couple together these towers. Like each tower on its own could not resist the lateral forces in theory, but connected they behave much better. And on top of the diaphragms, we have a pretty large steel trusses that connect in between the towers that aim to shed the load in between the towers and act as one. And you can see from the size, this coupling truss in particular, it's several stories high. And the sizes range from one, in this particular one is 1.8, but other trusses are 1.0 meter deep sections, so pretty deep, and they need to be developed into the walls. So in our case, given that we're a tripod, for our sake, we believe that the building for response spectrum was behaving pretty well. We also have translational pure modes in the first and second period, and rotational in the third. But all our pedals are inclined at different angles, so we had to do different studies of how analyzing it at different angles created changes to the way that we were getting results. I was talking a little bit about this before, but we don't have a peer review panel. We have an expert panel review, which it's a different word for something that's fairly similar. You have a series of experts that aim there to align the expectations of these very peculiar building objectives of design and what do we need to reach, and what is kind of a good agreement so the client gets what they want, and then the expert and we are kind of in the same alignment of the results that we're getting from the project. In this particular case, the building was designed with 7 ground motions. Here I'm highlighting only 6, but we use a total of 7. 3 of those are artificially generated, and 4 of those are narrow wave groups from their library. You can see here their code spectra for frequently earthquake versus the spectra for similar level on all the different ground motions and on our target periods. One nice thing about the Chinese code that the requirements for performance for specific ground motion level is kind of very clear. The only negotiations that now needs to take place with the parties is like where do we want to apply that? Are we over applying a certain performance range into the height of the building? And it's a very collaborative experience with the expert panel. The ground motions are need to meet certain minimum requirements to match the code level spectrum. And you can see from the distribution of storage here for the different ground motions that some of them go slightly above or below the response spectrum values. Drift-wise, we are lucky to have a very well-behaved building for seismic and for wind, but we still need to make sure that it meets all the criteria for the different ground motions. And I will talk later about another driving criteria that makes this building what you might call stiffer than usual, because you see a large gap here between the target drift versus the results of behavior on different time histories, is the acceleration criteria for the residential units that end up driving what we really need to have in this building. The elastoplastic model that we built for this project was performed using ETABS in lieu of perform, where we had fibers and hinges for coupling beams, and where we test them for the different levels of frequent, moderate, and extreme level earthquake, and in order to check the different criteria for coupling beams and shear walls. And it's as David said, it's good to see how you can start tuning up the system as you validate and go through the checkups of the ground motions in order to focus in the areas that really need to connect the building and provide also the additional level of performance for those extreme events. The wind by itself, it's another area where we had to push our envelopes quite significantly. Our original proposal, we stated that we can save material by having these openings in between the building. We did the right-hand side is a small model that we created for the wind tunnel that we have in our Chicago office, where we tested these ideas numerically and physically. But then the wind tunnel testing consultant in China created their much more detailed model to test this to nil, and also included the different future and current elements that impact the behavior of the tower. But we got very good results. The code only allow us to reduce the code level wind by to 80% of the code level. So we were able to meet and exceed that with the current geometrical configuration. The interesting part is like through the wind tunnel consultant interaction, we were able to obtain time histories for each one of the diaphragms of this tower. That was the main concern. What is the residential unit will experience? What is the users going to experience? And so there was a lot of focus on trying to get as much information on that. So we had more than 714 time histories applied to each one of the diaphragms. The integration of these was quite challenging, even more so than the seismic one. However, we are in a different range of of behavior of the model, where here we're not moving into nonlinear yielding of elements. We're more into acceleration, displacement. It's more about what do you experience? Like what's the serviceability of the building? So the runtimes are slightly different or quite different from the nonlinear ground motions that we run. And here's a couple of the results and the information extracted where we try to capture, like, of course, the extreme areas of the pedal, how much acceleration do we feel, and are we within the limits that the client has established that we need to meet. Lastly, once we have all this information from the seismic, the wind, gravity, construction sequence 2, we have a heavy focus on these coupling trusses that are connecting the tower and are key for the behavior of the structure as a unit. So separate models were created using Strand 7, where we model the steel with their detailing, concrete surrounding, and rebar to understand what is the interactions of these elements and how will they behave under upper and lower bounds of forces extracted from the prior information. And it's a great place to be when you can confirm that for different extreme level events or frequent level events, what is the different behavior of the building, and make decisions out of it of how we need to thicken or detail in a different manner these nodal regions. And you can check not only the concrete behavior as the previous one, but also the steel areas. We not only check that particular top chord connection, we also check the diagonal ones and with good results. And then the central pieces that are aimed to be expressed as a celebration of the structure rather than just a brace coming into the way of the architecture, as you will see later. Through all these design process, another thing that we kept in the back of our mind is how the evolution of the system and the design decisions that we're tracking through the time influence the carbon footprint that the tower has. And this was instrumental internally to our driver of, because it's different when you quantify the carbon footprint of a tall tower, and then that carbon footprint per square meter gets distributed, but a number of users that's quite large, so it becomes very efficient. So the more efficient you do this tall tower, the more efficient it would be in carbon footprint for the users in the future. So the end result of this structural system was quite unique for its future. These separated pedals working as one with these pretty big coupling trusses. It has other features that we can dive deeper into, but the time is not allowed. But I want to show you a couple of pictures of what the project wants to be. Right now, I didn't went deep into the foundation, but we have a pile foundation system, and that's in progress. But the project is quite unique, located in front of the lake, with awesome views. And here you can see how we're trying to celebrate the diagonal coupling truss as part of the amenity space for the project. And each one of the different typologies of coupling truss aims to do that, to be part of the architecture and connecting these pedals with the rest of the usage of the project. The crown has been a challenge on its own, and I think we're finalizing the CD comment package, so we're quite happy with it. But this is a different take on what pushing the boundaries, where the seismic and wind components of an analytical work aim to make the decisions made for the design that we're putting forward more effective, and also tell a deeper story that wants to be fairly unique. I think we have time for questions.
Perfect. Thank you very much, both, for the very insightful presentations. And I would like to open the floor for questions. So if anyone from the audience has a question, please feel free to unmute yourselves and ask. I can also see in the chat some questions from Professor Kostas Georgopoulos. Okay, so let's start maybe with the people in the audience. Ahmed, would you like to unmute yourself?
Hear me now?
Yes, we
Can you
can.
hear me? Yeah.
Perfect.
Ahmed Abu Ahmed from Jacobs. Thank you for this amazing presentation. Just a quick question, Ricardo, regarding strand 7. How did you define the boundary conditions? I see it's a partial model, it's not a full model. How did you go about defining the boundary conditions and making sure that it's kind of simulating the actual behavior?
Good. So, well, as any model, it's a partial truth. So we started with a planar model, and then a bigger model, and then measuring the reactions on the back of this partial model and comparing them against our larger ETAPS model. Boundary of what we call toy models, and this is kind of a toy model that's trying to represent a zoom version of a very specific piece, required a lot of bounding and trying out different conditions. In this case, we end up using a series of pin rollers in key specific zones, and it certain determined length of extents of this node in order to capture what we really wanted in terms of force transmission.
Okay, great. Any other? Any other questions? Neri?
Yeah. Hi, I'm Guido Neri from company Arup. I have a question about how do you see the integration of these very advanced analysis with the response spectra, and also looking at the analysis that we do usually at the beginning of the projects. So in the preliminary phase, how do we integrate this kind of advanced analysis in the preliminary phases of the projects?
That's a great question, and more and more we are doing it earlier, I'll say. We had a project, it's actually only a 2-story building, but we wanted to use a new seismic device. We did nonlinear response history analysis and schematic design to make sure that we could at least feasibly work through and understand the behavior with new types of seismic devices. There used to be a pretty high fee premium to do this kind of work. There's still some, but it's not as much as it used to be because a larger percentage of team members are coming from universities that introduce the topic, and we can usually get somebody doing a nonlinear model within their first 5 years. So using it earlier in design is always the best. Sometimes we'll just do it. Sometimes we'll talk with the client and make arrangements for that. Not all of them use it early on. Like that 500 Folsom one, we did that nonlinear analysis later in the design, and we had a lot of confidence in the design. And it just so happened that maybe that confidence was not well founded, right? So doing it earlier in design is definitely an advantage.
If I can, do you see some specific risks in this kind of analysis? I mean, in the early stage, or are every time a plus?
No technical risks. It's just financial. How much time do you want to spend on it? And you kind of frustratingly, the biggest inhibitor is usually having a geotech on board that can produce the ground motions early. That's actually usually the biggest inhibitor. Once we have ground motions, we can usually run pretty fast.
Okay, thank you.
Mm-hmm.
Professor Georgopoulos, would you like to ask your questions? Or otherwise I can read from the chat? Okay, yeah.
Yes, quite happily. I would like to do that. Good evening or good morning. I don't know where you are at the moment, David and Ricardo. Thank you very much for your excellent presentations. I delivered the CPD course on Eurocode 8 for seismic design for the Institute of Structural Engineers here in the UK. And every time that we come up to the question of tall buildings, I say, do not use it, because the spectrum of Eurocode 8 go up to 3 seconds, or periods of 3 seconds. So I was very interested to see a spectrum that you saw that goes up to 7 or 8 seconds. Mm-hmm. And presumably that's a spectrum given by the Mexican code, which is likely to be very close to the American code and that you use for a tall building in Mexico. But the accelerations are very, very small. Did you actually use those accelerations in the analysis of the building? That goes to David.
Yeah. Well, thank you for the question. Well, let me put it this way. I'm not too interested in the code spectra. Before ASCE 722, we knew the code spectras were off in California, and we just wanted the site spectra from the geotech. That's all we wanted. Like I feel like I can't breathe until the geotech gives me a site spectra. Like I don't really know what I'm dealing with. And they'll take the spectra all the way out to 12, 14 seconds without any problems because they're doing a site-specific spectra based off borings and various tests that they're doing on the soil. They have no problem creating a spectra quite far out there. ASCE 722, the code spectra got pretty good. Actually, we've had 3 projects in a row where the ASCE 722 spectra matched the site spectra quite closely. So well done, ASCE 7. I think you guys really hit it out of the park in 722. But yeah, it's really needing to get it from the geotech because I feel like I can't make good decisions until we get a site spectra. The project I shared was in San Francisco. I did mention Mexico because we've done a lot of work in Mexico, which is super unique and quite distinct from San Francisco. But one of your questions was the code has been revised
yes, I was
in
going to ask
Mexico.
on that one. On that one, I was going to say you didn't have the need to do a site-specific response spectrum for that tall building.
We did. We did site
Oh, you
spectra.
did?
Yes.
Site-specific.
Yes,
Okay.
and that's where we got it from. And
so you did
and
specific geotechnical investigations and you produced site-specific spectra, which is good to know. Yeah.
It's
The other question.
Yeah.
Yes. Go on, David. Sorry.
I was just going to say my advice to anyone doing work in high seismic zones: get a site spectra from the geotech, not a code spectra. Don't go to the owner, work it out. I know there's fee involved, but it's the right way to do it. Right.
That's the way I thought. Because if you look at the actual earthquake that happened in 1985, actually the accelerations those days were a lot higher. The actual acceleration was a lot higher than the one specified by the design spectrum. So I wonder, you mentioned there is a Mexican code 2022. Is that a new code in Mexico or you're talking about ATC7?
Which one? I was talking about the US code in 722.
The US code.
But Mexico does have a new building code. It came out in 2021, I think, or early 2022. It's very good. We've done several projects in Mexico, and the spectra that comes out of the code and the way it relates to your building, the spectra it actually changes based off the period of your building a little bit. I would actually say a little more sophisticated than ASCE 7. The Mexico building code is quite good now. Yes, quite good.
That's good for presumably short and medium height.
Yes.
Medium height buildings.
Right.
The other thing I normally tell my students is that I give them an example for a 17-story building in UBC Zone 4. With an extra 10% of the total cost, you can make it earthquake qualified. Because a lot of clients in a sort of low to medium, low to seismicity zones, or even high seismicity zones, they refuse to pay the cost of extra for the structure. So judging now from, say, the East Coast and the West Coast, what is the difference in percentage of the cost of the frame? Because obviously the East Coast is not earthquake qualified, the West is. Do you have a number that you can tell us? How more expensive it is in the West Coast, the frame, than it is for a tall building, than it is in the East Coast? Do you have something on your mind for that?
That's a great question. I'm not sure I have a good answer for it. I will say that the lateral systems on the West Coast are usually more clear and maybe have less transfers and things like that on the West Coast, which helps with cost. But I don't have a good number in terms of cost difference.
Okay. Thank you very much. If I may, I had a question for Ricardo, because that was an excellent presentation, Ricardo, and for China. And also, you had a slide on sustainability. And sustainability of tall buildings is a very controversial matter, whichever way you look at it. And I was wondering, do you suggest any ways of reducing the embodied CO2 of tall buildings? I mean, what are the ways of reducing it? Because that's the key there, the embodied CO2.
So I agree. It's a touchy subject. Although with the help of our urban planners here in our office, they have a very interesting white paper on the true, how to convey it. It's like what's kind of the true weight of sprawled design of housing versus densifying, and it kind of rings a bell with the taller buildings. Like if you have taller buildings, you can become more carbon efficient in a way than with a sprawl design, and therefore with all the needs of new housing, is that the right way of going? Of course, it has a very upfront cost of upfront carbon footprint. Are there ways to that? Well, I was kind of in the chat trying to reply to some of the questions. I think making it more efficient as a building, like taking the material off, of course, is the first one, but also designing it to the right level. Like with these tall buildings, you often have the chance of achieving a better performance criteria. You're not designing for collapse prevention, which is, I think, one of the drivers of a very unfortunate level of performance throughout. Like even though we're preventing the collapse, there's a ton of buildings that they need to be repaired and modified in the future. These buildings are designed for a much higher level of performance. Therefore, they are sustainable in nature. They're not going to be replaced by all means after a tiny earthquake. And then I think we have a white paper in our webpage related to different avenues on how to make buildings sustainable. I don't know, David, if you have the link for that one. I think it's do you remember the one that Eric did for? We can share it with Maria and maybe distribute it. It's kind of a white paper of different technologies, because in the end you need to support yourself holistically. It's not the engineer's role solely to reduce the carbon footprint. It's kind of a team effort. So that's why we try to show
it's great. I think the word, I fully agree with you on the efficiency side of things. That's what we're pushing here in the UK, the efficient design. And obviously you have to put material only where it's needed, which is the key here. But in China, by the way, I mean, just outside question, do they actually use sustainable concrete, all these modern concretes with cement replacements and all the rest of it? Do we actually use stuff like that, or just yeah?
I'm not sure, to be honest. Right now for this particular project.
The national and local governments are very focused on implementing that, although the U.S. is farther along in implementation.
Are you? And is President Trump is going to stop all that from happening? No comment. Thank you very much, guys. Thank you very much indeed.
Thank you.
We have a question from Benjamin as well. Maybe one last question, and then the time is getting for the meeting. So Benjamin, if you want to unmute yourself.
Yes, thank you for the presentation. I am Benjamin from Rice University. My question is, David, did you mention that recently you shift from Perform 3D to ETABS? Is that related to convergence issue? And what kind of model, nonlinear model, are you using for the shear walls? It considered like the shear flexural interaction of the shear walls? Thank you.
Yeah, good question. We no longer use Perform 3D. It's not because it was inadequate. It's just the workflow is easier when we're already in ETABS to step over with an ETABS model. We have a lot of in-house geometric tools using the API between Grasshopper and ETABS, which just dramatically improves our workflow compared to Perform 3D. All of the major features of Perform 3D were moved over as it relates to shear walls. And we did a fair amount of vetting of that. The downside of using ETABS is the file size is beyond painful. It's like the hundreds of gigabytes blow up really fast, and that's pretty expensive on Amazon servers. So that's the downside with using ETABS is the output file size is just enormous. There's still some firms that use Perform 3D. They think it's just more efficient for them, and that's fine. We've moved over to ETABS. And yeah, we use it for nonlinear fiber modeling, vertical elements in the core, and then we use lumped plasticity models or hinges, rotational hinges for the coupling beams.
Yes, thank you. But I mean, my question is like, I understand like the models for the shear wall that is in ETABS just consider like the flexural behavior. It's not like the flexural plus shear interactions.
Oh, yeah, good question. Well, maybe one thing is and this is the same in Perform and ETABS, is we're modeling vertical fibers that represent the rotational. We're not doing lumped plasticity rotational models for the shear walls, although I don't know too many people that are doing that anymore. But the interaction of flexure and shear, you are correct. It might be in ETABS, and if it was, I don't know if I would use it necessarily because it was a little bit tricky to use and Perform 3D. But it's not common for us to have flexural shear interaction in our models. There's a number of practices that do that. I have no issue with doing that. There's certainly, when it's done in a well-informed way, especially with a peer review panel, I think it can be quite good. But it's not necessarily common for us to do that.
Yeah, thank you.
If I really wanted to do it, I'd probably go back to Perform, if you're wondering, just because I haven't vetted it out in ETABS yet.
Yeah, maybe I can send an email to you.
Sure.
Okay.
Great. And if there are more questions, you can also email to Seced YMSC email address, and we can pass the questions to the speakers. So thank you both, David and Ricardo, very much for the presentation and sharing all this useful insight. And thank you everyone for attending. And we can now close the meeting with that.
Okay. Thank you.